and also the entire workshop. So it's my great pleasure to introduce Chile from Princeton University, who is going to talk to us about optimal gradient-based algorithms for non-concave bandit optimization. So please, Chile, take it over.
Thank you so much. Thank you for the invitation. I'm Chile from Princeton University, and today I'm going to talk about recent work on non-concave bandit optimization. So bandit problems are known as an online decision problem, where an agent will interact with the environment, only receives a scalar reward, and aim to maximize the reward. In a more formal mathematical way, I see. Yeah, I was trying to speak up. So every round, the agent will have some strategy and sample some actions based on the strategy inside some action set. And there is some unknown reward function, and the agent will observe the noisy reward, which is just the f of the action plus some noise. We usually assume the noise to be light tail. And our goal is to maximize the reward and at the same time minimize the regret. The regret is defined in this way, which is the cumulated sum of R star, the maximum and the best reward minus the current reward we receive. Okay, so bandit problems has a long history, maybe since 1930s, and got a lot of attention because it has many useful applications, including ad placement, recommendation service, to name a few here. In this talk, our focus is to how to go beyond linear and concave reward functions. Because although linear bandit has been very well studied, it doesn't have sufficient representation power. And at the same time, existing analysis on nonlinear settings are just suboptimal. We will see that in a few slides. Even for some quadratic problems, they're suboptimal. So our goal is to answer the following questions. First, what is the optimal regret for non-concave bandit problems, especially some structured polynomials? Yeah, so we focus on structured polynomials on one hand, because polynomials is a natural next step to go beyond linear. And with the degree goes higher, it will have better representation power. And remember that two-layer neural networks, if you have the activation as a polynomial, is also a kind of structured polynomial. And why do we look at structured polynomial? Because if we do not assume any structure, we do not expect to do any better than some simple algorithms like method of moment or just match the coefficients. Yeah, so we try to design some algorithms with optimal dimension dependence for a large class of polynomials. We will focus on the following types of bandit problems, including the stochastic bandit eigenvector case, the stochastic low-rank linear reward. So this formal definition will appear later when I talk about each of them, so don't worry about it now. And stochastic homogeneous polynomial, which is higher order than quadratic. I look at both symmetric and asymmetric setting. And also noiseless two-layer neural network, but it will not be covered in today's talk since it has nothing to do with sampling. So let's first look at quadratic reward, which consists of these two settings. First is the stochastic bandit eigenvector problem. The setting is very simple. We look at the action set where the action comes from a unit ball. And we observe noisy observations of f at at plus some noise. And for the eigenvector problem, the function is of this quadratic form, A transpose MA, where we look at M to be the low rank matrices, and we can have this kind of decomposition. Therefore, for this kind of problem, we immediately see that optimal action lies in the direction of M's top eigenvector, if the top eigenvalue is positive. But if it's not positive, we can do some shifting. So that's not the essential assumption, just for the ease of presentation. Okay, for this kind of problem, it actually attracted quite a lot of studies before. For example, Jun et al. And Lu et al., they developed some upper bound of this form, square root d cubed k times t. They also conjectured that this dependence on d is optimal. We will see in the next slide why they think about that. And we can also see that if k, remember k is the rank of the matrix, if k is 1, then the problem is reduced to a bandit phase retrieval, because we observe A transpose some vector squared. And for phase retrieval, it has also been studied a lot, and there is a lower bound of d cubed over epsilon squared to attain an epsilon optimal bandit among all non-adaptive algorithms, which is actually stronger than square root d cubed t, regress lower bound. And another type of algorithms include eluded dimension. With eluded UCB algorithm, which applies broadly, but specializing to this problem, they also get a square root d cubed kt regret. And the bandit PCA, still d cubed. Some other prior bandit optimization algorithms, either they do not apply or have worse bound. So why do we have this d cubed barrier? Let's first look at the simplest case, where the function is of this form, A transpose some parameter theta squared, which is just the rank 1 case, or named bandit phase retrieval. So with a random action, A sampled from the unit sphere, the expected reward is of order 1 over d. And recall that we assume the noise has standard deviation at least order 1. Therefore, the signal to noise ratio, or called SNR, is at most 1 over d squared. In the meantime, to learn the optimal reward, we will need all the direction of theta star. Since it is d-dimensional, it requires at least d bits to encode. So if we played non-adaptively, for each bit, SNR is 1 over d squared. We need d squared samples, and altogether, we will need d cubed samples to learn all the directions. So this is the intuition of previous result, why we have the d cubed dependence. But that is not a very smart idea. We can try to get around it, because at some time, we will have already get more bits of information which will help us to increase SNR. Suppose we are at the point that we have already learned S bits. You can think about that as you have already learned S directions of the theta star. Then you can make use of that to help you increase your SNR at this point to be S squared over d squared. So to learn the next bit, you will need d squared over S squared samples. So altogether, if we play adaptively, meaning you can change strategy based on your observations, together you can get a total sample of d squared instead of d cubed. So that's the intuition here. We assume at this point we already learned S bits. Oh. Yeah, it's just the dummy variable. Okay. Yeah. And we notice that noisy power method is just a practical implementation that help us to implement this kind of intuition or idea. I suppose people are quite familiar with power method. This is just an algorithm to help us try to find the leading eigenvector of a matrix. Suppose we have a random iterate and we will do matrix vector multiplication multiple times, and eventually it will converge to the top eigenvector. So in this case, we also want to do a matrix vector multiplication for multiple times. How to do that is like we observe that if we sample the actions that is centered at the current action A plus some random Gaussian noise, and we calculate the reward times the noise, its expectation is actually parallel to M times A. This means if we do the update summation RTZT, if we have sufficient samples, it will eventually concentrate to M times A. So if we do this update and repeat this procedure multiple times, this procedure is just similar to noisy power method. And we know that there exists some studies that show the convergence of noisy power method, and we can get a good convergence rate and a good sample complexity. So here we analyzed what we required. So for each iteration, to get a small enough noise, we will need d squared, kappa squared over epsilon squared samples to get an error of epsilon over kappa. And the total iteration, because power method has linear convergence, so the total iteration is log factor of d over epsilon. So the total pack complexity to achieve epsilon error is just the multiplication of these two, which is kappa cubed d squared over epsilon squared times some log factor I just omit here. This will make sure that the current action is of epsilon optimal to the target direction, which will ensure that the regret is actually less or equal to epsilon squared. And if we just do explore then commit algorithm, we can easily get the pack to regret rate of square root kappa cubed d squared times t. That's how we improve the d cubed to the d squared here. Okay. And similarly, we can look at another class of problem of stochastic low-rank linear reward. So in this case, the action set is a matrix where A lies in the D times D space, and we allow the Frobenius norm to be less or equal to 1. In this case, the noisy reward is of this form. Fa is the inner product of an unknown parameter matrix M times A. And again, we assume M to be rank K and symmetric, but symmetric is not essential. We can relax it to be non-symmetric. Yeah, and in this case, we can easily see that the optimal action A star will just be M divided by its norm. Okay, so in this case, to find the optimal reward or find the optimal action, we need to recover the whole M. But although M is of dimension D times D, it has the low-rank structure. So what we can do is a similar idea. We recover the right eigenvectors of M, and then it can help us to recover M easily. So here we will use an iterate X to approximately recover the right eigenvectors of M. Since the idea is quite similar, I will not discuss in detail, but what we do is with through noisy subspace iteration, this X will gradually approximate the right eigenvectors of M, and we will maintain A, the action, to be M times X transpose, where A will eventually be approximating to M because X will approximate to the right eigenvectors of M. And the whole procedure is very similar as before, just we changed the noisy power method to noisy subspace iteration. And with these two types of algorithm, we can get the improvement like this. So for eigenvalue problem, we also proved a lower bound of square root d squared times t. And Jun et al., they achieved this kind of regret of square root kappa squared d cube kt. And we improve it to be kappa cube d squared times t here. We also have a gap-free version, but the dependence on t is not so good. And for low-rank linear case, Lu et al., they proved a lower bound of square root d squared k squared t, where the upper bound has d cubed here. In our case, with subspace iteration, we get this kind of upper bound, but in this setting, lambda k minus 2 is of the order k. So this actually exactly match the lower bound when the matrix is well conditioned. So this is the result for the quadratic case. Next, we move on to higher order polynomials. First, I want to mention that for higher order polynomials, the problem by its nature is actually harder. Why is that? I just plot the surface of two-dimensional problems of this form, where Fa is A transpose A star to the piece power. So it's a piece order polynomial. You can see the surface here. For P to be smaller, we have more signal on average. But when P is larger, almost all surface is flat. So we have much fewer signals. Especially, we also observe a lot of noise. And with this procedure, when P is harder, of course, the problem is also harder. When P is larger, the problem is harder. And with mathematical language, it is because if we randomly sample the action on the unit sphere, the average signal strength is actually d to the minus p over 2's power. So when P is larger, signal is smaller. So now we can look at symmetric high order polynomial bandit, where again, the action set is where A lies inside a unit ball. And we observe noisy reward of this form, where the function f, the reward function, is summation of lambda j times Vj transpose A to the piece power. And we assume those Vg are orthogonal to each other. Equivalently, we can write it as a tensor vector product, where the tensor, we assume it to be orthogonal decomposable. And in this case, the optimal action will be A star equals to V1, the top eigenvector of the tensor. Okay, and then we do something similar than before, but there is some actual challenge here. So we hope that with this kind of estimate, again, we sample the action centered at A plus some random noise, random Gaussian noise. We hope that RT times CT will be parallel to the tensor vector product, but that is actually not the case. When P is large, this product will be, if you do some like Taylor expansion, it will have a lot of terms. But luckily, each term are all targeting to steering towards the target direction, because this is the combination of multiple tensor vector products. Each one will all push you towards the desired direction. So with this kind of algorithm, again, we can show that it has superlinear convergence towards the target direction. And we can show a regret of this form, square root d to the piece power times k times t. With similar idea, we can also extend to asymmetric higher order polynomial bandit problems, but let's just skip it because it's very similar. So now we look at the lower bound. We want to know if our algorithms are optimal. For the symmetric action set, we show that among all adaptive algorithms, the regret is at least lower bounded by square root d to the p's power times t over p to the p's power. So if we think about p, the degree of polynomial to be constant, then this matches our upper bound. For asymmetric action set, it is lower bounded by omega square root d to the p's power times t. So the dependence of d matches our upper bound again. Together, we can see all the results for the stochastic settings. So we have looked at 4 different kinds of problems, different kinds of structured polynomials. And for each kind of problems, the previous work on the dependence of d are all 1d worse than the lower bound. And we derived the lower bound. And with our algorithms, we can show that we find the optimal dependence on d. Although for the quadratic case, it depends on the eigenvectors. Okay, this is our main result. And we also want to mention that all the ideas can be extended to reinforcement learning in simulator setting. Recall that the Bellman equation is like this. So for a Q function, recall for reinforcement learning, we have a Q function for each state action pair. And based on the Q function, we can find the optimal policy, and that is our target. So if we learn the Q function, we learn what we want. And this is the Bellman equation. And we are looking at the following setting where we assume, so we exemplify the result with the eigenvector case, but for other type of polynomials, it also applies here. So we assume that the function of low-rank matrix M, and it's a quadratic function, this function is Bellman complete, meaning that with Bellman equation, it is closed. And we look at the simulator setting, meaning that at each round, we can freely query the state action pair and observe the next state based on an unknown dynamic function. And we also receive the reward R at the sampled SA pair. So for this setting, we can use the idea from our Bandit problems. We can treat that as an oracle, and we can estimate this M of the Q function. And with each time step H, we can estimate this M up to an epsilon over H error with order of D squared, K squared, H squared over epsilon squared samples. So overall, with all H time steps, we can learn the epsilon optimum policy with this sample complexity, which is this previous one times another H. In contrast, existing work requires D cube times H cube over epsilon squared. So we improved a factor of D when K is small, when it is well structured. However, this previous result is for online setting. We do not know yet how to apply our result to online setting, because unlike Bandit or the simulator setting, we cannot freely sample the state action pairs for online settings. In conclusion, we have found optimal regret for different types of polynomial reward functions, including stochastic bandit eigenvector, stochastic low-rank linear reward, and higher order homogeneous polynomials, and the noiseless two-layer neural network I did not mention today, but you can refer to our paper if you're interested. And the takeaway messages the following. First, like UCB algorithms, they are optimistic algorithms, but they can have suboptimal regret here. So from time to time, we may need to play suboptimally to achieve the overall optimality. And For a degree P polynomial, the initial SNR is already 1 over d to the p's power. So in order to get a dependence of d to the p, we will need some algorithm that is a linear or superlinear convergence rate to get around the optimal dependence on d. And also, since the initial phase is the hardest, we need to play adaptively and also consider some burning algorithms, which means we have some strategy at first. Once we get more signals, we change to another strategy. And we have also studied that, which will give us a better regret in some situations. And also in this work, we are considering convex and continuous action set. So it still has square root t packed to regret conversion with etc. However, for discrete and finite action set, we don't know yet how to deploy our algorithms. So for future direction, naturally, one is to settle whether the condition number dependence is necessary. We kind of believe if we want to achieve the optimal dependence on D, the condition number is somewhat inevitable, since you can infer it from optimization problems. And how to apply the result for non-orthogonal higher order polynomials. And also for discrete action set, I just described the challenge. And we conjecture that this idea can be extended to multitask representation learning for Bandit or MDPs. And that's all of the talk. Thank you for listening.
Thank you, Chi, for a nice talk. Are there any questions?
Yeah, very nice talk. So I wonder, in your algorithm, how did you do exploration? Maybe I missed that part. Do you need to do any exploration?
It's just explore then commit. So the noisy power method phase is the exploration.
Oh, okay. So it's a explore then commit kind of.
Yeah, explore then commit.
More questions? So maybe I have one. So beyond polynomials, I mean, is there any other structure family that you can, that is reasonable where maybe analyzing these questions would make sense?
Yes, of course, there are a lot of other types of functions we want to explore. But currently it's very hard. You see, since previously even the quadratic case, they did not get the optimal rate. So I think to look beyond that, first we can look at non-homogeneous cases and then to other more complicated functions. But it might be hard to directly look at very complicated reward functions. Yeah.
And I guess, so, I mean, one of the themes in the workshop is also optimization on manifolds. Is there anything in that direction that perhaps could be of interest to, the people who do optimization on manifolds that you could perhaps envision or that you were curious about?
Sorry, I think the last part I didn't hear.
Oh, I just asked about, if it could be perhaps meaningful to consider some of these problems on manifolds, given that maybe, I mean, as your state, your action space, and I'm just speculating, given that one of the topics of the workshop is optimization of manifolds.
I see. Good point. Although the cases I'm looking at right now for quadratic function eigenvalue problems, they have their real values in like online recommendation system, etc. I'm not sure if the manifold case apply to a real scenario. So, so I actually haven't think about that. Thank you for the question.
All right, so let's thank Chi again for a nice talk. And I wonder if any of the organizers wants to say final words.
We should all thank Elena for not only all the groundwork, but also putting together a very coherent program.
It remains for me to thank also Santosh and Philippe for lots of help in putting all of this together. And thank you all for showing up to this workshop. I hope there was something useful for everyone. And we saw many interesting open questions, and for people who are participating in the program, these are all on Discord. So I hope that there is also some nice work that is going to come out of all these discussions. So thank you all, and we'll all keep in touch, I hope.